What's going on, guys? How are you doing? Let me know if you're here, because it says there's 19 viewers but the live chat isn't actually showing anything. So let me know if you're actually here, if you are here already. Ain't nothing coming up in the live chat just yet. Could just be because you have not said anything yet, but just want to make sure. Usually people are like, yo, 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 yo. Three likes, 18 viewers. Yeah, just give me a shout if you're watching. How's it going, everyone? Hope you're enjoying your week so far. It is Wednesday, middle of the week, midweek stream, as you do. Just going to be taking a look at this kicker, KX-1500.1, as the first thing for today. Going to see what's going on with this bad boy. Good afternoon, NSV. You are indeed. Scammer Ruby. Love to see it. Right, let's have a look at this then. So we have a kicker KX-1500. I think this is, what's this? Yeah, ZX-1500.1. We have output drive circuit here, which wasn't actually screwed down. There was a missing screw from there. Interesting. I wonder if that's got something to do with why this amp's in with me, because it looks like it might have wiggled its way back a little bit. Looks like it's been worked on before. We have some solder on this op amp here on the drive card. Some resistors as well that look like they've been replaced. This capacitor as well, possibly. Yeah, lots of evidence of replaced components around here. Interesting. Okay. Still not getting any live chat through from you guys. I struggle to believe that there is 26 people watching and no one chatting. So I'm just going to go ahead and close this live chat and refresh this. There we go. Now it's come up. Must have been some glitch with YouTube. Okay. There we go. There you guys all are. I thought I was streaming to myself here for a minute. How's it going, everyone? Let's have a look. See what we got. Here we got. Yo, how's it going? Oh man, I can't seem to scroll up now. Oh, there we go. Gidrius, Shyam, how's it going? How's it going, Steve? Jamie, what's up? What's up? What's up? All you guys, thanks for jumping on the stream. Hopefully, going to be a good one this afternoon. Got a few bits to look at. Yeah, literally, I block every number afterwards, but you know, they always have new numbers, don't they? What's up from Oklahoma? Alright, so yeah, this amplifier, I believe, has come in, and it's been, a repair has been attempted by a previous technician. I've also got some kind of tape on this transformer over here. It's possible that this transformer was rubbing on something, maybe. Okay, I think the first thing for us to do is to power this up. I don't think we've got any dead output FETs or anything like that, but let's just give a quick check first. I left my multimeter downstairs. Let me just go and grab my multimeter. 1 second. Right, multimeter is here. I've been busy today filming an episode of Boom or Bust that should be released tonight, guys. Should be released tonight. I've been doing them every Friday, but I'm trying to do them 2 times a week now. So there'll be one on Wednesday, one on Sunday. That's my schedule, planned schedule for Boom or Bust. Wednesday and Sunday, hopefully, provided I can keep it up. Alright, so do we have any shorted outputs? Let's see. Nothing there, nothing there. This is definitely output side, isn't it? Yep. Okay, not getting any shorted output FETs. Now the output drive circuit is likely to be this thing right here. Let's have a quick peek underneath it. 74 HC 74. Okay, yeah, that's definitely output side. And the driver itself has an LM319, another LM319. OP1656, nope. My multimeter is crying for a new battery. Where is the actual final driver? It could be this thing right here. No, maybe not. Maybe it's this one right here. There we go. Okay, so the drivers for the output MOSFETs appear to be over here. Yeah, got one there and one down there. Okay. Right, so yeah, no dead FETs. We're safe to kind of give this some power, see what it's doing. I've got a feeling this might be a bit of a headache amplifier, which is good for live stream. It gets us engaged, doesn't it, with you guys. Any updates on the Proton? So the Proton currently is unwell, it's poorly, and I need to do some work on it. We had a really cold week a couple of months ago. It was like -6 degrees, and I don't think the Proton had enough antifreeze in it. So what's happened is the coolant has expanded and cracked the heater matrix. So there's a very small radiator that's in the passenger footwell, like inside the dash, behind the dash, that forms part of the heater. Obviously it uses the heat from the engine with the fan, blows nice warm air into the cabin. So that radiator has cracked, so it's leaking coolant into the cabin, and obviously as a result of that, you're getting air bubbles and air locks in the cooling system, and the coolant is like leaking out. So obviously I can't run the engine because it will just overheat. So I need to. It's going to be a pretty big job. I need to pull the whole dash out to replace the heater core, the little radiator in there. So that's going to be a massive job. So yeah, Proton's not doing so well at the minute. Sad times. Sup Eberg, how's it going? Thanks for jumping on, appreciate you. What about the bass van? Yeah, I still have that. I use it. I'm using the bass van as a daily at the moment because the Proton's no good. So I'm driving the bass van every day. I don't bass it every day though. Like I very rarely use the subwoofers. Like the subwoofers just stay off the whole time. not really a super full tilt bass head anymore. It just gets a bit loud. Okay, so let's give this some power and see exactly what the output section is trying to do. I suspect we're going to have massive headaches in the output section with the drive circuit and whatnot. So let's first of all build a little bit of rail just to make sure that we're building both positive and negative rail. Let's tune the scope to high frequency, LF reject, 20 volts divide. Okay, so there's a bit of positive rail by the looks of it. So let's have a look at the one next to it. Next to it's probably a low side. Low side. low side as well. Okay, looks like we've got probably 3 high side FETs. Yeah, 3 high side FETs and 3 low side FETs by the looks of it. So we're going to probe a low side FET and see what it's doing in regards to Class D switching. Okay, so we get a bump to 12 volts. Look at that on the scope screen. So then probing the low side drain just now. So as soon as the relay engages, there's a bump to 12 volts. It's actually slightly after the relay engages that we get a bump to 12 volts. I'm curious to see what's on the speaker terminals before the relay engages. Anything on the speaker terminals before the relays engage? Nope. Okay. Although that bump to 12 volts seems to possibly appear before the relay engages as well on the speaker terminal. So I'm probing the speaker terminal right now. So the speaker terminal should be completely isolated from the output section at this time until the relay engages. But I'm sure that I'm seeing this start to rise before I hear the relay click. A little bit, yeah. It's hard to tell. Bypass the heater coil and you can drive the car. Yes, that is another option that I'm trying to do. I can't get the hoses off of the pipes that go through the firewall. They're like, the rubber is like stuck, so I need to try spraying some like oil type stuff down there and like prying it off. So yeah, that's a temporary solution, just to get it driving for the meantime. And obviously in the summer I don't need the heater, so that could be a good temporary solution as well. I could just use it for the summer like that and then fix it in the autumn time. Okay, so how do we go about diagnosing this then? Let's have a think. So we're not getting any output switching, we know that for sure. So the first thing would be to do is to check we have all of the required voltages going into this card here. This card here is going to be the one that's probably taking the audio signal and converting it into pulses for the output section to work with. So let's check that we have plus minus 12 volts here, plus 5, and make sure there's no DC on the input coming from the preamplifier circuit either. Okay, negative 14.9. Ah, hold up. That's interesting. Okay, positive 12. Positive 14.9. Right, now what seems to be happening here is when the relay engages, okay, the whole kind of ground reference for the output section is shifting up by about 12 volts. Can you see that? So if we look at plus minus 12 volts, I'm going to use the other probe as well, just to probe both of them at the same time so you can see it happening, okay? So we've got our 2 bipolar supplies here that the drive card's going to be using to work with. So if you take a look on the scope screen, I'm going to turn the amplifier on. Powers up. We've got our nice bipolar supplies there, plus minus 12 volts. However, as soon as the relay engages, both of those bump up to a new floating ground point that's about 12 volts above ground. Now that shouldn't really be happening. That is potentially an issue that might cause there to be all kinds of nonsense happening with the output section here. So what we need to do is figure out why that's happening. Now that seems to be something, it seems to be related to the relay. So when the relay engages, that's when the ground level shifts. So that could just be a coincidence, but that could be related. So I think I might actually turn my attention to the relay engage circuit. But before we do, I'm just going to make sure we do have our 5 volts present before the ground level shifts. Yep, we do have our 5 volts before the ground level shifts. We got a bunch of other pins here that are labelled. I'm just going to see what they're doing, if anything. Not much. How about the preamplifier circuit, all the op amps over here? Let's have a look to see whether the ground level bumps on there as well. So we have our op amps here, pin 4 and 8 should be our supplies. Negative 14.5, positive 14.5. Just make sure there's no DC on any of the audio pins of the op amp. Not until that ground level shifts. Okay. Okay. So let's find a reference for ground. So this, I think this is a half bridge amplifier. So the speaker negative terminal, okay, shouldn't have any DC on it whatsoever at any time. If it does, then it's proof that there's a ground level shift here. So I'm just going to turn this on and probe the speaker negative terminal. Yeah, there you go. Look, we've got 11.3 volts on the negative speaker terminal. That just means that the ground reference level for the output section is different to the power supply's ground reference level. So that should not be the case, and that might be causing some issues. So I think what I'm tempted to do is actually strip this board out of the case and just have a look for like broken traces underneath. Just have a proper good old visual inspection of the board and see what the jam is, see what's going on underneath it as well. But just while we're here, let's remove this output driver card for a minute. And let's just power it up without that present. Just see if the ground level shift is the same or not with that removed. Probably will be. Yeah, it is. It's still there even with that removed. So it looks like a previous technician has attempted to replace a bunch of components on this, but I don't think that was the issue originally. That was probably just like stabbing to try and find what the issue was, but not, you know, kind of barking up the wrong tree. I don't think that that's the issue. So yeah, I think the first thing we should probably do is just give this a good old visual inspection and then maybe try and strip the board. One thing I have done in the past with issues like this, where we've got a ground shift between the output section and the main power supply section, is actually to run a wire from the speaker negative terminal to the main power ground to like physically tie the two grounds together to stop the output one shifting. And if it does stop the output one shifting, then sometimes the amplifier starts working, or sometimes the voltage that it shifts to actually has some current behind it, and whatever the issue is on the amp starts getting hot, and then we're able to see what's causing that voltage shift to the output section ground. So yeah, just a quick visual inspection just to see if anything funky is going on. Got any dead traces, blown resistors, anything like that. It's interesting that it seems to happen when the relay engages, so it's kind of tempting to think that it has something to do with the relay engage circuit. Now the power supply control circuit is down here, and the relay engage circuit is usually also down here amongst the power supply circuit here. So just a quick visual inspection for any obviously burned surface mount resistors or anything like that. I'm not really seeing anything here. Over by the relay, no, not really seeing anything there either. So I think the best thing to do just be to strip the board just to make sure there's nothing funky going on underneath, because sometimes issues can be hiding under the board, and it also makes it much easier to trace where the different components are connected to. Like, I don't have a schematic for this amp. I might be able to find one, but it's still going to be easier just to strip the board at first and have a look, see what we can find under there. Just got to wait for the residual rail voltage to dissipate. We've got about 20 volts still sitting in the board here. So you just wait for that to dissipate. Maybe I can find a nice big point on the board where the rail voltage is, so I can quickly send it to ground. There's negative rail. Positive rail there. Negative rail there. There we go. There's our 2 points. So I can just take a big dummy load, big resistive load. Shove that in there, shove that on there, short out those rail capacitors. Now we shouldn't have any residual voltage on the board. Nope, nothing on the positive, nothing on the negative. Excellent. Right, let's start stripping this thing then, see what we can find underneath the board. Any plans on doing an SQ build? So the build in my Proton is an SQ build. It's not it's not an SPL build in the slightest. It's fully SQ, which is really nice. I actually really enjoy listening to the build in the Proton much more than I do in the van. Do they have salt and lemon candy in the UK? I can't say I've heard of it, although it might be under a different name. But I'm not a massive like candy sweet kind of person. So Daniel Doria says, can you tell me what goes in Q100 and Q102 under the board? Under the driver board, you mean? Oh, Q101. I've got Q101 and Q111. Is that what you mean? Yeah, that's the only ones I can see that are similar to the numbers you're referencing. Got Q13, Q12. So yeah, like I was saying earlier, I've got a boom or bust this evening. So I was releasing boom or bust videos every Friday, but I'm going to bi-weekly. So now there's going to be a video on Wednesday nights and Sunday nights, provided I can keep up with them. So I've just finished editing episode 7 this morning. Pretty excited about that. It's a good one. You'll enjoy it. It is a good one. Next to the 4426 chips, I've got Q100 next to the 4426 chips. Q100 and Q102. Okay, I'll have a look. The parts that are in this board is a D669 next to the Q100 is a 2SD669 in this board. I'll check the other one as well once I get the preamp board out. What's up, Living Loud? How's it going, buddy? I'm alright, thanks. I'm all good. Hope you're well. Looks like a Kicker ZX. Yep, that's absolutely correct. It is a Kicker ZX-1500. Do you plan on a dual boom or bust setup ever? Dual sub? Yeah, so basically for season 2, I am planning on doing that as two 12s, like two 2-inch drivers, so that people can do some wacky kind of hybrid band pass designs and all kind of stuff like that. So yeah, I think season 2 will either be a single 15-inch driver, that being a 2.5 inch, or a pair of 12s. I haven't decided yet, but I think we're a little way off of season 2. I think season 1 will last a fair while yet. Got plenty of submissions to get through. Okay, it's that side out, and I suspect we might need to remove the preamp board entirely to get this out. Would you say it's easier or harder working on kicker amps versus others? So because kicker amps are not typically a generic circuit layout, you generally tend to have less experience with them. So like the kind of generic Korean and Chinese boards, they are found in so many different amp brands that you tend to work on them more often, therefore you tend to get more experience with them. With kickers, you only work on a kicker layout when you're working on a kicker, so that's just one brand. So you tend to work on them less. So this circuit layout, for example, I'm much less familiar with. So I would say this is probably harder to work on than some other brands, just because it is a entirely bespoke layout. So therefore I have less experience with it. It doesn't necessarily mean that the circuit is any more advanced to work on or like any harder to find faults. It's just you tend to get less experience with them. When you're getting the mini subwoofers that actually look like a scaled version, not sure. There is a guy that I've been speaking with who is working on building some tiny little speakers, some 2.5 inches that actually scale up really well to a real subwoofer with all the correct parameters and stuff like that. So like I say, I do plan on having, so he's working on 2.5 inch drivers, not 2 inches, so that scales to a single 15. So season 2, maybe we'll do dual 15s for season 2. How do you feel about that? Obviously with dual 15s, the amount of space you'll have in the cabin is going to be the same as what we've had for season 1. So it's going to be quite compact. A lot of the enclosures that you guys are going to have to design for dual 15s are probably going to be having to be sensible sizes. None of this like crazy 8th order massive bandpass enclosures that take up the whole space for a single bloody 12. You're not going to be able to do that with if you've got a pair of 15s that you've got to fit in there somehow. But it still might be really interesting to see, and I think it will allow for some kind of interesting like maybe some isobaric designs as well. We'll come in with some isobarics and all sorts of stuff like that. So yeah, we'll see. I just realised I don't actually need to remove these standoffs. These standoffs are screwed in from the other side. The only things I need to remove are these 3 screws here on the main board. Okay, Daniel, the other one is a D669 as well. So yeah, it's a 2S D669 or KS D669 on the board next to the drive ICs, in case you were wondering. Okay, let's get this out of its case now. I think that's all the screws out. Yes, it is. Out you come. Thank you very much. Okay, so now we've got a good view of the bottom of the PCB as well. Now we didn't necessarily need to take this out of the case, although looking at this, there wasn't any thermal paste on the output FETs, so it's a good job we did remove that. You don't need thermal paste for MOSFETs that are mounted to the heatsink with these thermal pads, like these kind of squishy thermal pads. However, if you're using just Mylar tape, like this really thin Mylar tape stuff, then you absolutely do need thermal paste because it doesn't squish. So yeah, that won't have helped any, done any favours for it. Let's have a look. This has definitely been repaired before. I don't recognise this though. I don't think this one's ever been in my workshop before. I don't recognise these parts really here at all. and I don't recognise any of the parts that were changed on the driver card or any of this previous work, so I don't think this has anything to do with me. Interesting. Okay, so why do we have a level shift on the output section when the relay engages? We're going to flip the board over and have a look and see where the relay goes to. So this is the relay. Flip it over, have a look at the coil contacts here. So the coil contacts for the relay appear to be these two right here. So we have one trace that goes over here. We have a little transistor just there, which is hiding underneath the preamp board. And the other pin for the coil, is that just going to ground perhaps? Output side ground? No. Main side ground? Nope. What does the other side of that go to? There's no trace on the bottom side here, so we have to look at it from the top. Well, it has continuity to this diode, so we can at least go from the top now on this diode. Now, usually, one side of the coil will go to a ground or a 12-volt supply, and the other side of the coil will just go to whatever circuit's controlling it. Okay, well, let's power the board up and just see what voltages are actually on this relay here. Thanks very much, Gidrius, for the 10, man. Top man, keep good work, and thanks for the support where needed, man. Anytime. Massively appreciate the 10. Thank you so much for that, buddy. Really appreciate that. What kind of compound do you use for the MOSFET to heatsink? I just use whatever this is. This thermal paste here. Silicon grease, 1.4 watt. It's like pretty cheap, 1.4 watt meter Kelvin. It's not like the best thermal paste, but it doesn't have to be super incredibly good for these amplifiers, because the thermals kind of ramp up gradually rather than being like an instant spike like you see in a CPU, for example. So yeah, it's not super critical, and you end up using loads of it on these amps. So if I was like using really top tier computer repair thermal paste, it would just be so expensive. Alright, so yeah, let's power it up and just see what's on the relay coil contacts here while it comes alive. Okay, so as we turn the power supply on, bearing in mind I haven't actually applied the remote yet, we get 12 volts on the relay coil. That's pretty standard. That's pretty typical. What you'll find that you have 12 volts at all times on both of pins of the coil. Then when the relay wants to turn on, a transistor will ground out one of them, so that therefore you get 12 volt potential across the coil. So that's what this transistor is going to be doing here. We're going to have 12 volts on there, and then we're going to have that connected to ground on one of the other pins. Yeah, so that's going to be sending that to ground when it's ready to. Let's just power the amp up and see. Okay, yep, so this one will go to ground. Huh. It's really interesting. I was expecting it to like sink down to ground nicely, but it actually has this kind of waveform on it before it hits ground. Have a look at this. Have a look at this. So this is the relay coil. Just before it sinks to ground, it has this waveform on it. Oh, I'm going to try and catch it on the scope. Oh, I keep missing it. Come on. Ah! My reaction time isn't good enough. No, one more try. No, I can't catch it. I'm not fast enough. But yeah, that's definitely not normal. I'm a bit confused as to why that would be. So let's probe the other pins of this transistor that's next to it to see whether that does anything funny. Okay, nothing funny on this center pin. That's going to be ground. This first pin, this is the one that's probably going to be controlling the relay turn off. Oh, there's nothing on that either. That's weird. There's nothing visible on either this pin. Nope. Anything visible on this pin? Nope. Like, there might be some current there, but it might be so it might be so low that we're not able to see it on the scope. I've come across this before. Eh? Wait a minute. Oh! This transistor is actually just supplying this side of the relay with 12 volts. It's this side that's going down to ground with the square wave on it. That's weird. That's a little bit confusing. So this transistor has 12 volts on it on one of its legs for this pin of the relay, which stays up at 12 volts. This pin of the relay sinks down to ground, connects to this diode here. Right, so we need to find out what's pulling that down to ground. So we need to trace this. Okay. Let's have a look at the power supply section for a sec. I want to see what the power supply drive looks like. I want to see what the waves coming off of the transformers look like. So power supply FETs are all over this side. So that looks pretty nice. Yep, looking good. Looking good. Looking good. Looking good. So power supply FETs all look good. We have the rectifiers over this side, over here. So let's have a little play with the rectifiers right now. So if we zoom out a bit on the scope, we can see we have 113 volts there. That's our AC out of the transformer. I want to see if this jumps up at all. Okay, it does. So the AC out of the transformer bumps up. See that? Interesting. Okay, what I'm going to try doing, I think, is taking a piece of cable and connecting the speaker negative terminal to our main ground reference. Okay, I want to see if anything funky happens, if the amplifier fails to turn on, if anything starts heating up, etc. Because yeah, I'm not really seeing any sort of failed components that would cause this at this time. There should be some coupling between the output side ground and the main side ground anyway. There's either usually some kind of resistance, either 100 ohms, 1000 ohms, or it's capacitively coupled. Yeah, okay, let's grab a little piece of wire and connect these two grounds together and see what that does. So the speaker negative terminal is over here. Just drop a piece of wire in there. Hello from Kenya, do you need a scope to fix amps? Absolutely yes. You might be able to get away with without using a scope to fix amps, but you would need to know what things would have looked like on the scope, so it's really, really hard. You do definitely, in my opinion, need a scope to fix amps. Possibly not so much Class AB. You could probably get away without using a scope for some Class AB repairs. But for Class D, you absolutely need a scope. Right, so I'm currently connecting the output side ground to the main ground. We're going to see if the current draw rises from the power supply when that kind of bump happens up to 12 volts there. So let's probe the, let's probe something. Probe the, I don't know, what should I probe? One of the rails, one of the rectifiers here perhaps, over here. See what that does. I'm going to turn the power supply voltage down from 12 volts, just keep things a little safer. I'm going to go for about 10 volts, just keep the rails a little bit lower. Okay, so it's working fine. We only have 1 amp worth of idle current draw. So with the grounds connected, the relay engages. I'm just going to kind of time the relay. The relay engages before we have full duty cycle on the power supply. So we get relay engage and then it kind of snaps to full duty. So if I disconnect the two grounds from each other now, so they're not connected anymore, is that the same amount of time between powering on and the relay engaging? Yeah, it's exactly the same. Okay. Let's put the driver card back in. Let's just see if the amplifier does anything different or behaves any differently now that the grounds are connected together, so we don't have this shift. So let's probe the output, the low side drain of the output FET here. Power it up. Okay, so no Class D switching at all. Okay, let's keep the two grounds connected for now because that's not going to throw us off the center tool. Let's try and figure out why the output section isn't oscillating. We'll zoom in here on the drive card here for the output section. So we know that we've got plus minus 12 and plus 5 volts. OCP, overcurrent protection. Let's have a look and see what voltage is on that pin. We have 4.9 volts on that pin. Now I don't have a reference for what that's supposed to be. I don't know if that's supposed to be high, supposed to be low, or whatever. We have plus DRV. Let's see what that's supposed to be. That's 4.9 as well. Let's just check that ground is actually ground down here. Yep, ground is ground. Let's have a look over here. We have in, which should be nothing, so we've got no preamp connected. Okay, no, nothing over here, nothing over here. Negative DRV is about 0.3 volts. Okay. So we have a HEF4060B chip just here. I want to have a look and see what's on this. Now we should start seeing some kind of pulses. I think this actually, see this here, Y200, this is a crystal oscillator. So this should have some kind of pulses and some kind of oscillation on it to set a frequency. Oh, yeah, we've got something there. There we go. So we've got some oscillation, we've got about 2.5 megahertz. Okay, so that's what's probably going to be used to set the output section switching frequency, but it will be a derivative of that. It won't be like, obviously that won't be that fast. So this is possibly what the HEF4060B might be responsible for doing, is stepping that down to a usable frequency for the output section. So we've got 13.7 volts on one of the pins there. Aha, here we go, starting to see some PWM now. So we've got 2.4 kilohertz on there as well. Now we've got 9 kilohertz on there. So it looks like, yeah, this is definitely dividing this PWM down. 4.8. That's the high frequency from the crystal oscillator. That's extremely high frequency from the crystal oscillator. So yeah, it steps it down. Looks like we've got high frequency, slightly lower, slightly lower, slightly lower. It's kind of dividing it down every time. And then this is even slower here. This is 611 hertz over here. Okay, so that's kind of working as intended. Now let's have a look at what's on this op amp over here. Pin 1, we have some PWM. We have a triangle wave. Okay, so this is going to be the op amp that's probably going to be listening to the audio coming in and converting it into pulses for the drive circuit to use. I'm glad the triangle wave is working. There's our VCC. Nothing on there. Nothing on there. Nothing on there. Nothing on there. Okay, so we don't have like a square wave output from this, but we might not because we're not actually giving it any audio yet. So I'm not sure exactly how this circuit is working in that regard. But we should have, if I give it some RCA signal, we'll be able to follow that those pulses a little better through the circuit. I'm just going to go over here and just quickly probe the output driver here, just to see whether we've got anything on the driver. 5.7 volts there. That just seems to be constantly there even after I've powered the amplifier off. We've got 5.7 volts on pin 2. And that's disappeared now. Five volts on pin 4 as well. Nothing on pin 5. Nothing on pin 6. Nothing on pin 7. Oh no, pin 6 does have something on it. Probably has like rail or something. First to nurse says you're wrong. Even with 0 input, you should have output on the op amp since it compares it to triangle wave. Okay. Creating PWM. Right, okay, thanks very much first to Anur. That's really, really useful info. So possibly that op amp might be bad. Got 10 volts on pin 6 of the driver down there. But okay, let's turn our attention then to the op amp. So there should still be PWM output from that. Right. So pin 1, we have our triangle wave. Pin 2 is what it's comparing it to, and pin 3 is the output. That's what it should be, I assume. So pin 2, we don't have anything. And pin 3, we don't have anything either. Pin 4 is negative 14. Pin 8 should be positive 15. Make sure that I'm getting VCC. Yep, we are. The other side of the op amp, we have negative 14 plus 1 and plus 0.6. Okay, I'm going to remove the op amp just there because that could be wrong, like we have in the live chat. First tuner saying that this should have output even though there's no RCA signal. And I want to see whether we should have 14 volts on pin 7 or not, because that could be damaged op amp. It could be sending low negative VCC to pin 7 for some reason, or it could just be on the board already. So I'm going to remove that op amp and just see what it does without the op amp fitted. Maybe just replace it and see what it does. I think you could probably use a TL072C here. That's the most common op amp that's used for comparing the audio wave to the triangle wave to get pulses. Triangle wave is plus minus signal. Comparing to 0 volts on the other pin creates PWM. Nice one. I really appreciate that, man. Thank you very much. That's really, really useful. Gives us something to go by. Wait for my hot air gun to heat up a little bit. Okay, it should be hot enough now. Didn't really feel very well soldered. I'm wondering whether all the pins were actually making a connection there. It just kind of came off really quickly. Right. So I'm curious to see whether we have the 14 volts on pin 7 even with the op amp removed first. Just want to see whether that was meant to be there or not. So power up, we have 14.1 volts on there, and on pin 7, oh no, pin 7 we now have negative 2. So yeah, that possibly was not supposed to be there, possibly. It could have been a bad op amp. So we still have our sort of triangle wave now on pin 1. It's different shape because it probably hasn't got a load on it from the op amp. Pin 2, oh no sorry, pin 1. Pin 1 has this triangularly shapy kind of wave on it. Pin 2 also has a triangularly shapy kind of wave on it, and pin 3 has nothing on it. Okay, cool. So let's try replacing that with 072C, see if anything changes. What are these? 4052C. Let's see if these would be any good. I've just got these, the 072Cs. I'm not sure if I've got any that I know are absolutely good. Oh no, I do, I've got a bunch of new ones. But see, the thing is, I've got these new 072Cs, but whenever I've tried using these specific ones that I ordered, I never really get good results. I get best results when I take a 072C from a donor board. So I'm a bit skeptical about these ones. Like, I've never really had that great success with them. So I've got these ones, which are 4052s. I'm just having a quick Google just to see whether they're the same pinout. Oh no. Nope, they're not the same pinout, I don't think. Oh no, wait, hang on a minute, maybe they are. 4052, here we go. So the pinout is in one, into, out. The one I just removed was an OP1656. Okay, so the pinout's the same, so I imagine it will be okay. Pretty high speed, etc, etc. Should be fine. Excellent video performance, low distortion, so it's probably fine. Just wanted to say I love the Boom or Bust series. If I knew what I was doing, I'd enter. Man, thanks man, appreciate that. I'm glad people are enjoying the Boom or Bust series. Let's try one of these 072s first that I've got here that are brand new, just out of interest. I want to see how they do in here. Rather than using the hot air, I'm actually going to solder it just manually with the iron, because I've found that they're very sensitive to temperature, these op amps, and using the hot air, I have actually, even being very careful, managed to damage these op amps in the past. So I'm just going to use the iron for this one, just to manually solder these legs down, see what happens. Okay, so yeah, that was very little heat on the actual chip itself, but that's soldered down nicely. Let's get some isopropyl to get rid of the flux. Not that this flux is conductive, but it's just a bit neater, isn't it? Allows us to probe it a bit easier. Okay. So the first thing I want to do is power it up, and I'm actually going to probe the low side drain of the output MOSFET, just to see whether any nonsense appears on there. So if nonsense appears on there and we don't notice it, then it could be bad. So let's probe the low side drain first and power it up. See what happens. Okay, we did actually get a little bump there on the low side drain, interestingly. Let's do it again. Not any bump there this time though. Looks like there's possibly an attempt to build some switching. Oh yeah, there was definitely something there, so we've got something there now at least. Power up. A little bump. Oh, yeah, little flashes of switching. yeah, we're getting little flashes, little attempts at switching. So what I'm going to do now is just double check and see what we've got on the op amp itself, and then I'll try applying a load to the output speaker terminals and maybe some signal to see if that will kickstart the Class D switching. Sometimes it needs a bit of kickstart, but I just want to see what's on the output of this op amp now that we've replaced it, see if we've got any output as was suggested in the live chat. Is 9.9 volts enough? That is another possibility. The amplifier might need a bit more voltage to start the Class D switching, so we'll give that a go as well in a minute. Okay, so there's our triangle wave. Nothing on pin 2. Nothing on pin 3 either. That's a shame. I thought we would be getting something there, at least. What about on the other side of the op amp now? Is that 14 volts back on pin 7? No, we've got negative 12.9 now. Interesting. We are getting some attempts at switching though, so what I might do is I'm going to crank the voltage up a touch and apply some signal, because sometimes applying some signal and seeing how the amplifier behaves can help you to diagnose drive circuit faults and such. So I'm going to connect this preamp board back here and give it a bit of signal and see what that does. Is this self-oscillating? Don't think so, because we have a crystal oscillator and a this IC here which steps the frequency down to something that the amp can use. So I don't think it's self-oscillating. Looks like we do actually have a fixed oscillation frequency. I'm decoupling the two grounds from one another as well just now. Okay, so the preamp board is connected again, and let's get our RCA hooked up to the input. Input left, 35 Hertz. Keep the level nice and low. Input level low, auto turn on 12 volts. Okay, so let's see what giving it a bit of signal does. Okay, it does seem to do something. Yeah, as I increase the gain, I've got a little bump of DC on the low side drain there. There's very, very faint attempts at some kind of switching going on. Yeah, you see that there? Just a tiny, tiny attempt. Interesting. Okay, so I'm going to remove the preamp. Well, I'm going to remove the RCA because that's definitely not helping the situation here. Okay. What I'm tempted to do is to disconnect the output FETs from the circuit so that we're just working with the output drive circuit, because that can sometimes really help in getting a drive circuit fault like this to show up, or to kind of follow it a lot easier without risking damage to the output FETs. So I think what I'm going to do is I'm going to just remove the output MOSFET gate resistors We do have pull down resistors. It's very important that we have pull down resistors across the gate and source when doing this, otherwise the MOSFETs can spontaneously turn on and all explode if they're not pulled down, if there's no pull down on the gate to prevent them from phantomly turning on. So it's short out the rails there, and let's get a little bit of flux on the gate resistors and just pull them to one side so the MOSFET's no longer connected to the main board, and then dive in a little bit with the drive circuit, see if we can figure out why it's not switching. I still think it might have something to do with this weird jump in ground position, but not too sure what's causing that at the minute, so we're going to keep going with this potential drive circuit fault. Is this the F16B52 Type 1 periamp in Perry's guide? I don't think so. It might be a kind of more modernized version of that, possibly, but no, I don't think so. Once I've removed these resistors, I'm going to learn the circuit a little bit. I'm going to follow the pathway of the gate back to the driver card here, so we know all the components along the gate path, so that we know what parts to maybe check or have a look at and probe and stuff like that. So yeah, we're still getting the jump from ground with the new op-amp in. Yes, still getting that. Okay, so that is all of the gate resistors shifted for the output FETs, so they're no longer part of the circuit. Just want to make sure that we do actually have some resistance between gate and source here. What's the 473 for then? There are pull-down resistors that are 47,000 ohm, but they don't seem to sit. They go through the gate resistor first. So although there are pull-down resistors here, I just need to bridge over the pad there. Oh, that's annoying. So there are pull-down resistors, but they're after the gate resistor, like on their way back to the driver. So I'm still going to need to run a little bit of wire between the gate and the source, because otherwise these FETs will spontaneously turn on. Question for you, Sam. Amplifiers make volt amps. I believe the rails make the voltage simplified. Now what makes or supplies the amperage? Nothing makes or supplies amperage. Amperage is a demand. So when you power an amplifier up, the voltages are present. And when you apply those voltages across a resistance, then depending on that resistance, being the subwoofer, current is demanded. The voltage across that resistor will demand a set amount of current based on the amount of voltage and the amount of resistance. Now it's down to the amplifier to supply that current. The amplifier will supply infinite amounts of current until it breaks, or until some limit is reached in the amplifier whereby some circuit then limits the voltage to prevent any more current being generated. So current in a car audio setup comes from the vehicle supply, so the alternator will create voltage and be able to supply X amounts of current. The battery is floating at 12 volts and can supply X amount of current before the voltage starts dropping. So the current is a bit like the amount of water in a bucket. The voltage is how fast that water can exit the bucket, or how much pressure there is in a hose pipe, for example, connected to the bucket. So nothing generates current. Current is there or it's not. It's yeah, the amplifier doesn't really care. It doesn't know how much current is there. It will try and supply as much current as the load demands with the voltage across it until some limit is reached, whether some component limit and it breaks, or whether some voltage drop limit reaches and the amp turns off due to protection or something like that. I'm going to do this under the board. It's just going to be a bit easier, I think, to connect these little jumper cables to the gate and source of these FETs, prevent them from turning on. Actually, you know what would have been way easier? Probably just removing the drive ICs, but I wanted to make sure they were still part of the circuit so I could diagnose easily. I hope this repair doesn't take too long. I need to do the thumbnail for tonight's Boom or Bust episode before it goes up as well. Okay, so all of the gates for the output FETs are now connected to the sources. So with the gate resistors removed, that's cool, they're out of circuit and they shouldn't spontaneously turn on at any time. Since a lot of amps have capacitors rated a tad over the potential rail voltage they can do, wondering how to look at an amp to see how much current it can supply by the parts installed. Not really. but how much current it will. So basically what you can do, you can look at the rail capacitor voltage limit, and provided you know that it uses bipolar rails, you can work out roughly what the rail voltage potential will be, and from that you can take a good guess at how much AC voltage could be generated on the speaker terminals before clipping. So once you know how much AC voltage the amplifier can generate before clipping, then you assume that the amplifier is, say, 1 ohm stable. So then you put the voltage, the AC voltage on the speaker terminals, which you can calculate based on the plus minus rail potential. So the plus minus rail potential is peak to peak voltage. So from that you calculate RMS voltage of an AC sine wave between those two rails. Then apply that to the formula with the ohm load that's going to be driven on the outputs, and from that you can get how much current will be passed across the circuit at clipping point based on all of those assumptions. Okay, so output FETs are removed from the circuit now. I'm going to power the board up and I'm going to have a look and see what we have on the scope now along the gate path that would otherwise be leading to the FETs. I'll turn the voltage down a touch as well. Just probe the low side drain just to make sure that the FETs aren't randomly turning on for whatever reason. I wouldn't, like, they shouldn't do because they're disconnected from the board, but yeah. Okay, cool, we're good. So let's have a look then on the gate drive down here, see if we've got any pulses or anything like that coming from the driver card. So nothing there, nothing really there, just a bit of noise, nothing there, nothing there. Now we're seeing DC here, but that's just the shifted ground reference, isn't it? Okay. I'm going to common the output side ground with the main side ground to make this easier to work on, because it's hard to see, look on the scope screen and try and work out what I'm looking at when the ground reference is shifted so much. So I think this rail forms the output side ground. It's labelled SGND. Yep. So if I just run a small piece of wire from that to main ground, which is maybe over here somewhere perhaps, that's 12 volts, that looks like ground. Yep, so I just need a small piece of wire from this rail here to this rail here, and that will just connect the grounds together while we're working on the circuit here at least. fuck's sake. I just want a nice quick way to connect these freaking things together. Jesus. Is that too much to ask? Just let me connect these 2 points together so I can continue working on it. Right, there we go. Now what was the other rail I was connecting that to? Over here, okay. Oh my god. What is with this trace? It's like such high thermal mass. The board doesn't feel that thick. Just need to make a tiny connection between these two ground points. Sheesh. I've heard of Kevin Mansky. Yes, I have. I chat to him sometimes on Facebook. He asks me questions about amp repair and I try and help him where I can. Right. So now I shouldn't have any bump on the ground reference of the output section. So let's work our way back from the output gate then. So we have our low side FETs over here. Let's remove the preamp board to make it a little bit easier to see. So low side FETs over here. So the gate goes through here into this pin of this drive IC. Okay, now what is this drive IC? Let's have a look at the model. Is a can't quite see what that is. Is it just a 4429? Four 426S. Right, let's bring up the data sheet for that. So we have out A, out B. The inputs are directly opposite. So in A and in B are directly opposite the outputs. So 2 and 4 are our inputs here. Okay. So our inputs are this one and this one. So let's have a quick look at the two outputs. So this one's going to the low side here. Where's this one going to? That one and that one. Okay, so one of the outputs is going to these two FETs, and one of the outputs is going to just this single FET here. So it looks like we have three FETs per bank, but we're split up into a pair of FETs on one of the outputs and a single FET on the other output. Okay, it's weird. Don't know why they wouldn't just like parallel them or use one of them only. Now the input to the IC, where does that go to? Is that anything to do with this transistor? Do we go through a resistor here? Looks like we have a 621, so a 620 ohm resistor here. Okie dokie. The inputs are paralleled. Okay. This to me looks like an optocoupler. So we have an optocoupler here by the looks of it. This is a 601 or a 836S. Continuity to pin number 1, 2, 3, 4, 5, 6. Okay, so I'll try searching 601 optocoupler, and then I'll try searching 836S optocoupler. Maybe it's this. That looks like the right kind of shape. If pin 6 is some kind of output, then we know we've hit gold. (601), here we go. Pin 6 is VO, which is, looks like it's the output maybe. Pin 8 is VCC. Okay. VE, VO. Signal comes in plus minus here. Pin 2 and 3 is plus minus for the signal input. That diode then picks up the signal. VCC sent to VO. VE is probably enable. So yeah, I think that we have hit gold here. I think that is the correct part. So pin 2 and 3 are the inputs here to this optocoupler. Okay, so let's continue on having a look at pin 2 and 3 and see where they go. Okay, is any of these connected to ground perhaps? Or negative rail? Nope. So pin 3, does that go anywhere interesting? Got this diode here. So we've got a diode across pin 2 and 3. Okay. Let's go for pin 2. Let's see if pin 2 goes anywhere. Right, pin 2 has continuity to the other op-amps pin 2. Pin 3 doesn't have continuity to the other op-amps pin 2. So I suspect that pin 3 is probably the one with the signal on it, and pin 2 is the ground reference, because otherwise, why would you wouldn't have the two inputs for the high and low side connected together, because they'd be different signals. So therefore pin 3 must be the one with the signal on it. Alright, let's trace back further now then. So now we know that our signal's coming in there on pin 3. let's go a bit further back and see if we can figure out where pin 3 connects to. Might be a resistor in the way, so we've got a 3, what's that, a 361 or something perhaps there. See whether we have any continuity to any other parts of the circuit over here. Okay, nothing there. So we do have this resistor with a via that goes under the board. Aha! There we go. Now we have continuity to the driver card. Okay, fantastic stuff. So that is negative DRV and positive DRV. So that's what those markings are. Negative DRV is low side drive, going to pin 3 of this optocoupler, and positive DRV is high side drive, going to pin 3 of this optocoupler over here through the vias under the board. Let's just make sure that we do actually have continuity to the pin 3 over here via a resistor of some kind. 391, yeah, there we go. Okay, fantastic stuff. Let's just check the resistance of these. 383. Aha! I think I found the problem. Right, so by each of the optocouplers there is a resistor that is in line with the signal coming from the driver card and the optocouplers pin 3, which has the signal coming in. The resistor that is in line is marked 391, which is 390 ohms. The one on the low side looks a little bit strange on top, and when I measure it, we're not actually getting any resistance there. It's just completely open. We've got 1,500 ohms. Now that would prevent, probably, the signal correctly getting to that optocoupler. So, therefore, I reckon that it's either just this resistor or some other components on the low side drive circuit over here that have failed, causing the drive to not make its way to the MOSFETs. So let's remove that resistor. Yeah, it's definitely supposed to be a 391. Now, 390 is a bit of a strange resistance. I don't know. I don't think I'm going to have one of those just kicking around to quickly throw in. I could probably throw in something similar, like a 470 with maybe a 470 with like something else in parallel with it to bring it down to about 390. Let's go to a parallel resistor calculator. Just have a look. So let's start off with 470, which I know I definitely have. What do we need to get that down to about 390? Maybe like 1,000 ohms, something nice and easy. 319, yeah, that would work. 1,500, or maybe 2K maybe. Yeah, maybe a 2K. Yeah, either a 2K, 2.5K, or 3K will bring it down to about 390. Perfect value would be about 2,500. So I guess I'm going to have a quick look on some donor boards and see if I can find, well, I know I have a 470 in my resistor box, so I need a 470 and then I need something around about 2.5K. Oh Daniel, you're so clever, use a variable resistor. Why didn't I think of that? I always forget that variable resistors exist in the times of need. Yes, I will use a potentiometer. Of course. Why would I not? I don't think there's any issues with high frequency switching PWM going through a variable resistor like this. Maybe I'll use a 470 and then use a variable resistor to calibrate it down I think that's probably the sensible thing to do. So this is a 50k, yeah, that'll be fine. So yeah, I'm going to drop a 470 in, and then I'm going to solder a potentiometer across it to calibrate it down to about 390. So should have maybe a 470 in here somewhere. What's that? Nope. There we go, there's a nice cheeky 470, that'll do. Bit of flux. A little bit of fresh solder on these pads, I think. Yeah. Okay, cool. And now let's just solder the potentiometer across it as well, so that we can calibrate 390-ish. Living loud with Andy, got to jump off. Glad you figured it out, Sam. No worries, man. Appreciate you. Thank you very much. I assume we're going to probably have some more problems. I assume that the resistor is unlikely to be the only issue. Because, like, why would this resistor fail randomly by itself? So we're going to have a look and see what... Oh, fuck. There. The bloody hell. Going to see what other components might be dead around this area. Because there might be some other stuff dead around here. Okay, there we go. I think we have the potentiometer soldered. I'm just going to quickly change the battery on my multimeter because it is absolutely toast. I'm surprised at how low voltage I can get away with still running in this multimeter. Like, it's a 9-volt battery. I'm pretty sure the voltage sitting across that 9-volt battery is about 4 at the moment, judging by the sound. These rechargeable batteries I use, I'm swapping one from my component tester to my multimeter just now. The one in my component tester is also low, but it's not as low as the one in the multimeter. So the multimeter should still work even though the battery's a bit low. I just need to remember to charge them. I always forget to charge them overnight before I come back in the workshop. Right, let's turn this on. Ah, so much better. Instantly better. How much voltage was left in this battery, this 9-volt? Oh, 8.07, but that's unloaded, so it's probably cranking down to like 5 or something probably. Right. So let's calibrate a resistance then on this board for this thing here. So we've got 456 just now, so I need to reduce that until I get to 390. Unfortunately, you can't see the multimeter. I apologise for that. I haven't got my multimeter camera set back up. Oh, 385, 389. There we go, 389. So there's 389 ohms on that now. What about on the other side? Let's just check that. 351. Oh, maybe it's a 360. Oh no, it's a 390. I was reading the wrong one. 391, 382 on the other one. Yeah, cool. So that is now calibrated. Okay, let's check some of the other components around this area. Why would that resistor randomly die? What's this diode saying? Okay, 908 one way round, 509 the other way. Let's confirm that on the other, on the high side. 903 one way round, and we should have 500 the other. 532. Yep, that diode appears to be pretty much within spec, I would say. Okay, let's check the 10 ohm resistor here. Yep, that's correct as a 10. We've got a 621. Yep, that's within spec. That capacitor, let's check that that's not shorted. 515. 900. Check these two diodes. 517. Yep. 629, probably about right. This capacitor here seems alright. 361. 440. 361. 440. Yep, that's corrected in spec. 621. That looks good. That looks good. 666. Yep, okay, now why would this resistor be dead then, randomly? Oh, it's come unsoldered, of course. We have the signal coming from here to here to here. So is there any shorts on the optocoupler itself? Any low resistances? Maybe? No, doesn't look like it. Weird. Okay, I guess I'm going to power it up. Remember, the MOSFETs still aren't connected to the board at this time, so we're not going to get any output switching. But I just want to see whether we have any visible PWM making its way to the optocoupler, maybe through the optocoupler, anything like that. Cool, 390. Okay, so yeah, let's power it up and see whether there's any pulses coming through the optocoupler to the gates of the MOSFETs there. If there's not, then I will possibly just try and connect the MOSFETs back up. It might need the load from the MOSFETs to get the whole thing kick-started, not sure. Like I say, with these kicker ones, I haven't worked on tons of these before. I think this might even be the first drive circuit fault that I have done a repair on one of these, so I'm kind of learning this as we speak with this board. My component test has a 9-volt plug spot, so I plug it in. Ah, well that's much better. I wish my multimeter, honestly, I'd love my multimeter to be ran off the mains. It'd be so much easier because the batteries, you just go through them, don't you? Okay, so yeah, let's have a look then, turn the power supply on and see if we get pulses on the input to the optocoupler over here, which would actually be on negative DRV over here as well on the driver card. Okay, so no visible pulses on the scope screen. No visible pulses on the gates either. Nothing on the low side or the high side. So plus DRV is 5 volts DC on the high side, and nothing down here on the low side. Now, like I say, it could just be because this needs a bit of signal to get it kick-started, whatever. So I'm going to, without the MOSFETs fitted, I'm actually going to go ahead and plug back in the preamp board and apply a little bit of RCA signal. I just want to see whether applying some RCA signal gets some pulses on plus or minus DRV. Probably minus because that's the low side. Okay, cool. That preamp board is reconnected. Plug in an RCA. There, input level is low. Awesome stuff. 35 Hertz is going in, so let's have a look and see if we can follow the pulses through this drive circuit now. Negative DRV, see what we got on there. Okay, still nothing on negative DRV. Oh wait, we're getting something now. Ah, there we go. So there are some pulses that do briefly appear on the scope, especially if I quickly turn it up, although they're gone now. So there was a couple of pulses there on the scope screen initially. I wonder whether it needs to... Oh, there we go, they're back again. There we go. So we are getting some pulses there, negative DRV, but I need to feed it with like a fair bit of signal to get that to appear. But that could be a good sign. Oh, we're getting pulses on the high side as well. That's interesting, not used to seeing that. Let's check to see whether they're coming through the driver, the drive IC. Yeah, they are. The pulses are coming through the drive IC. On the scope there, you can just about see, but only when we apply like a proper fair bit of signal. So I'm wondering whether it just needs the FETs present to kickstart oscillation. So I'm going to go ahead and reconnect the MOSFETs now. to the circuit and just see whether it comes to life, whether that was the only issue, that random bit of that random resistor that was dead there. If not, then we have a few more issues to look at, probably on this driver card here. Okay, let's short out the rails again, bring them nicely down to ground. Cool, okay. Let's do these gate resistors back into place. Last one. Okay, that's all the gate resistors reconnected. Luna, I just tried to send you money. Wow, but it did some weird Google account crap. Do you have PayPal? I do have PayPal, man. Luna, thank you very much. I really appreciate that. I'll drop my PayPal. That's the PayPal. Really appreciate it, Luna. Thank you very much. No worries. Alright, cool. So, let's see if this starts to oscillate now then, shall we? I'm going to turn the signal right down, so I'm not really... Actually, no, let's remove the RCA completely. Let's see if it can start oscillating by itself without the need for all that. So let's probe the low side drains, see what happens when we try and power it up now. We were getting some attempts at pulses before, even though I couldn't really see it, so I'm quite hopeful that this will work. Let's have a look. Okay, nothing yet on the MOSFETs. Okay, nothing at all on there. So let's try applying the RCA. A little bit of RCA signal. Because we definitely were getting pulses to the FETs at one point there. I'm going to put my goggles on just in case the FETs decide to explode. I'm just going to put the goggles on here. Alright, let's have a look. Wow, nothing at all. Oh! What an idiot. Just remembered why that won't work. Does anyone remember why that's not going to work? Who remembers why that's not going to work? So that's not going to work because, remember, I shorted the gates to source to prevent them turning on earlier, but when we had removed the gates. I completely forgot about that, so I need to remove those. Obviously it's not going to switch. Jumpers, yep, Eclipse, you're right, jumpers, that's the reason. Okay, well that should be a little bit better now. Let's see what it does now. Now that we're not forcing the FETs to stay turned off. Let's remove the RCA, start again, remove the RCA, no signal help at all. See whether it wants to turn on. I'm going to give it 11 volts. Not quite going to give it the 12 volts just yet. Yeah, give it about 11. Okay, ready? Here we go. Hey! Ta-da! That is freaking awesome. Really strange though. Why weren't we seeing any pulses at all? Like, it's really weird the way that this circuit obviously works. So on these amps, just food for the memory bank, on these amps you don't get any pulses on the low side or high side gate with the MOSFETs removed at all, unless you absolutely crank the input RCA signal for some reason. But yeah, that's cool, great, love that, excellent news. Now we can go ahead and put a screw, because I don't like how this is flapping around so much, a screw in there. Oh, but also obviously I need to put some kind of permanent resistor in there, because I've currently got the potentiometer, so I need to I'll probably just order some 390s. I'll have a look on some donor boards. I might actually just by chance have a 390 on a donor board somewhere, which would be great if I do. But so yeah, the issue, so this amplifier, like I said at the start of this repair, has had loads of stuff replaced by a previous technician on this driver card here. That wasn't anything to do with the fault. The fault was one tiny resistor that was out of spec further down the line. But it can be quite hard to find that kind of issue. Like, it didn't really show any visual signs of failure. It was just kind of chance by we were working our way back down the drive circuit that we spotted it, and were able to measure the resistance of it. This was a good live stream, not the same old circuit. Yeah, this was a great one for me as well. This was a good one for learning this this circuit. I've learned a bit about how the drive circuit works on these boards now, so I'm a bit more confident for future repairs. Yeah, great stream, great repair. Happy with that. So yeah, just need to replace the resistor. What else was I going to say? We do still have the weird issue on this amp though, with the grounds being a different potential to one another. I don't know if that's something I need to resolve, or whether that is I don't know if that's actually an issue or like that exists, or whether that's just how these amps are anyway. So I do have the output side ground and the main side ground connected on the bottom of this PCB at the moment with a jumper wire. So I might remove that and just see if the amp still comes on and switches. And with that removed, I want to see whether we get any voltage potential on the RCAs, because obviously you don't want that. You don't want a potential difference on the RCA ground. That will just cause all kinds of headaches, noise, potentially damage your head unit. So that might be a little secondary fault that we might need to quickly sort out now that we've fixed the output drive circuit. Just going to do a little visual inspection one more time, just around the components here. I mean, if these surface mount resistors are dodgy, then it's if they have a tendency to go bad, then it's possible that there's a surface mount resistor that's responsible for coupling the output side ground with the main side ground that's actually gone open itself. It could be capacitively coupled, but it doesn't really explain why we've got DC voltage appearing there. I'd be interested to know whether the DC voltage that appears on the output side ground has any current behind it. Like, if it's just a kind of floating residual like ghost voltage, then if I touch it with my hand and touch ground, if it dissipates to zero just from like my body resistance, then we know that it has no current behind it at all, and it's probably fine. It's probably just something that just generates a bit of voltage on it by itself when it's left open. But yeah, I do want to investigate that a little bit more. Man, Daniel Dorrit, thanks so much for the $2, my man. Appreciate you. Thank you very much. Oh, and thanks for the 8 as well. Man, awesome. Thank you very much. Luna just sent you $20, £15. Yo, please keep me anonymous. Don't worry, I will keep you fully anonymous. Thank you so much, Luna. I really appreciate that. Appreciate you. Very kind of you, buddy. Yep, just got that come through now. 1563. Nice one, buddy. Thank you very much. Tried to send 10 and it sent 2. What kind of enclosure do we get to see in tonight's Boom or Bust episode? You'll have to wait and see. It's a good one. So let's just remove this. See if we can see if this ground shift is an issue or whether it's just fine. Fixing amps is hard work. It can be hard work, you're not wrong. It can sometimes be relatively simple, but yeah, it can be hard. Like this fault that this amp had was quite hard to find. Like, it wasn't a complex fault, it wasn't a complicated issue, it was just a resistor, but to find it was probably quite hard. And yeah, like I say, one technician already failed to find it. So I do feel quite happy. I do feel quite happy that I did find that, because that's cool. Okay, so the little ground jumper is removed from the board now. I'm going to go ahead and check to see whether there's any ground, any resistance between these two grounds anyway from factory, like as it is. So if we probe the speaker negative terminal, which is just here, and probe the main ground terminal, which is just here. Okay, there is, well, there is some resistance. It is changing. I've got 159 kilo ohms on the multimeter just now, 158, 150 something. Let's flip the probes. If that's the same, then we know it is a resistance rather than a capacitance. Oh, no, I think it might be a capacitance. So when I flip the probes round, we now have fully open, so it appears to be capacitively coupled, I would say, because the resistance is different depending on which way I put the probes. Okay. Okay. So, if I power it up now, again, I'm just going to power it up and make sure that it still comes on and still switches. Okay. Low side was, what was the low side? I think it was over here. Yep, still comes on and switches fine. The ground plane does shift up. So now what I'm going to do is I'm going to clip the oscilloscope probe onto somewhere, onto the board, so I can keep an eye on it. And I'm going to put my hand between ground and ground, and that will put my body resistance across the two grounds. And if the ground level falls on the oscilloscope, then we know there's no real guts behind that voltage, and it's probably fine. Let's just check to see whether the voltage does appear on the RCAs though. We don't really want any floating voltage on the RCAs, on the RCA ground. Ah, there is. It bumps up to like 10 volts. So there's 10 volts on the RCA ground shield. Right, yeah, let's see whether it actually has any guts behind it. So if I clip my oscilloscope probe onto somewhere, where is my clip? I want my clip. Find my clip when I want my clip. Here is a clip, that'll do. So yeah, let's clip this onto the I don't know, somewhere easy to clip it to. Some kind of ground point would be nice really, but just going to clip it to one of the output FETs here so we can see the switching, and the switching should jump depending on whether the ground plane shifts or not. Oh my god, it just won't stay anywhere, come on. Right, what am I clipping this to? Let's just choose a random fucking thing. Yeah, that's the relay, you don't want to clip it to that. Right, let's just clip it to that, fuck it, okay. Let's see if that shifts. Yeah, okay, that shifts quite heavily. So if I put my finger on the speaker negative and the ground over here, let's see whether that shifts or not on the scope screen when I touch it. If it does, if it falls back down to ground, then we know it's fine. No, it doesn't. Okay, so there is some actual guts behind that voltage there. That is making its way onto the output side ground. Ah, interesting. This is like another completely unrelated fault that might be a bit tricky to find. Like, if the voltage is making its way onto the output side ground plane as a whole, how would I go about finding that? Finding what's putting it there? It does kind of seem to be related to the relay a little bit. Like the ground plane shifts when the relay engages. Okay, I'm going to flip this board back over. I'm going to remove the output drive circuit just to prevent the output FETs from switching, just because we know that's working now. So I don't just while I'm diagnosing this new problem, let's remove that. So let's tack that onto there. Let's get my jumper wire as well. I want to see if there's any spark. I want to see if when I connect the two grounds together, we've got 10 volts worth of potential between the grounds. I want to see if there's any spark there between them when I connect them together, because that'll be interesting to tell me how much current is actually behind that 10 volts there. So if we power it up again, that's right. Yep. How many volts are getting to ground? We've got about 10 volts. So I'm just going to see if there's any spark when we connect the grounds together while it's powered up. No spark at all. And there's no change to the amount of current drawn by the power supply either. So this is measuring the output side ground now, okay? So it's noisy. We have power supply noise. We have power supply switching noise on it at first. This is the power supply coming alive. Then when the relay engages, we go up to about 10.4 volts. There's no difference in amount of current drawn, whether the grounds are connected to each other or not. Oh yeah, use a DMM in current mode to see the amount of current that is there. That's a great idea. Very clever, Eclipse. Nice one. Appreciate that. So it's, yeah, turn my multimeter to current mode. We're going to go for a current amps and we're going to go for 10 amps. Whack it on the highest setting. Move my probe over to the 10 amp hole. I think this works. All right. Okay. Cool. And now let's put the multimeter between these two ground points and see how much current is actually able to shift between these two ground points here. Okay, well, I've got 0 red on the screen there. I don't actually know if my 20 amp mode works. Oh, sorry, my 10 amp mode works. Let's put it on that 200. Let's try that one. Still showing 0. See, I'm not actually too sure though if my multimeter's current mode actually works, as I don't really ever used it before, and I'm just getting 0 on the screen the whole time. I should be able to read something just from touching the probes. I've got it on super sensitive right now, so that I should be able to read something at least, shouldn't I? Let's test the multimeter by turning the power supply down to like 0.5 of a volt with like super low voltage, like maybe like 0.2 volts, and super limit the current. Put the multimeter onto 10 amp setting, and just see whether it picks up any current if I short out the power supply with the probes. So yeah, let's go right down to like 0.2 of a volt there. Okay, no, there's actually no continuity. So when I short out the power terminals, yeah, I think the fuse in the multimeter might be gone or something. When I short out the power terminals, the power supply should be like, oh hey, you're shorting out, and you know it should be like, it should show me that there's a bunch of current being drawn. Oh, there is. Hang on a minute. Oh no, it is working now. Okay. Nope. Yep, we've got 0.4 amps. Okay, so that is actually working. Yeah. Okay. So that is working. .1 amp. Yep. Okay, that is working. So in that case, I guess that just means that there's barely any current behind the voltage thing across here. I'll turn that back up to 12. What I'm tempted to do literally is actually just put the jumper wire in and keep it there, like, or I don't know, some resistor, maybe like a 100 ohm resistor or something like that, or like a 1000 ohm resistor. Yeah, I've got absolutely no current, nothing red on the multimeter at all. But when I connect the multimeter, does the ground point actually shift down? I'll have a look at the scope. Okay, it doesn't, so that's not connected there. Do that and that back on 10 amp mode. Okay, yeah, so the voltage is sinking back down. On the multimeter, yeah, I've got 0.00 amps, so like nothing at all. Yep, 0.00 on the multimeter, so whatever current is flowing to ground that is not important. It's not worth worrying about, I don't think. So I might throw a 1K across these two ground points just to kind of keep it locked. Yeah. So I'll probably just throw a 1K across those two ground points just to get rid of that DC, but still keep the output side ground a little bit separated from the main side ground. But yeah, I think we're pretty much done with this repair now. That was quite successful. I was thinking this one might be a massive headache and might take me like days to fix, but no, I'm quite pleased. It's gone quite well. All I need to do, like I say, is just replace the surface mount resistor with one that's the correct value rather than the potentiometer that we've got fitted at the moment. Probably fit a 1K across the two ground planes just to get rid of that weird DC that's floating there. Put it back in the case, test it, make sure it's all good, and then we're going back to the customer. Sure seems like you're missing the 1K secondary common bounding. Yeah, absolutely, that's what it seems to be. There's no, when I measure the resistance between the two ground points, there is no resistance. It's like there's a capacitance there. But I don't have a schematic for this amp, so I'm not sure whether there is supposed to be a 1K resistor somewhere between the two ground points, or whether there's not, or where it might be if there is. I did have a visual inspection for burned 1K resistors earlier. Maybe what I'll do is I'll just have a quick look for it. Let's have a quick look to see if we can find a resistor that has output ground on one side and main ground on the other side. So if we probe the speaker negative, which is the output side ground, which is just, it's actually this bar here anyway. So this is the output side ground. SGND. Are there any obvious big, small little traces coming off that? Going all the way over there. Ooh. Use the thermal camera. I don't think the thermal camera is going to help me here. The board screws. The board does have a ground connection over here on the power supply side. It does have a ground screw to the case, to the chassis, but there's no ground screw or ground like connector for the output side ground to the case either. Right, let's have a look, see if we can find a resistor here that's connected to the output side ground on one side and the power supply ground on the other side. Sometimes they're around here. Aha! Ah! Okay, over here, there is this part here. Now this is a jumper resistor-y thingamajoob. It looks like a resistor, but it's supposed to be 0 ohms. It's just used as a jumper. Okay, where are we? Okay, see this? This is just used as a jumper. So this has continuity to the output side ground on one side. Now because it's a jumper, I should also have continuity on this side, but I don't. The other side has continuity to main ground. So the two grounds are supposed to be connected together, but something in this amplifier's life has happened to cause this little fusible resistor-y thingy, I guess you could call that a fuse, that has failed. So all we need to do is replace that, probably just with a really thin piece of wire, to be honest, at this point. So cool, two completely separate issues with this amplifier solved. Yeah, so to be honest, it's just a jumper, so I'm just going to replace it with a thin little jumper wire, thin enough so that if there is any catastrophic failure event where high current is trying to be dumped from output side ground to main power ground, this little piece of wire here will fuse open still. It's still a higher resistance than the traces that are carrying the current, so that's the whole point of those anyway. what you could also do is, because this amplifier seems to now obviously have the output side sharing a common ground with the main ground, if you were getting alternator whine as a result of that, you could replace this resistor, or this like jumper bar, with like a 1 kilo ohm resistor, for example, which might help, depending on the rest of the system, alternator whine and noise from existing. Yeah, cool. So yeah, that's all sorted, all done. Nice. Anybody got any questions before we head off? I've got a few bits to do the rest of today. Oh, it's a beautiful day outside. It's beautiful and sunny. Have a look out my window. Have a look out my window. Look at that beautiful sky out there. Lovely, lovely day. It's not that warm, not that cold either, but not that warm. But the problem is it's freaking windy as anything. It is properly windy to the point where I was struggling to open the door of my van earlier. So yeah, it looks lovely, but not the biggest fan of that. Don't like it when it's super windy like that. So yeah, there we go. That's all sorted. So I've got a few bits on the racks, as you can see. Got an SPL Dynamics D5 to do at some point soon. Lots of amplifiers all still boxed up. Got a big one there, not sure what's in that. There's the 3D printer. There's the box for Boom or Bust that we just filmed. So I'll be printing the next enclosure probably this evening. I always print my enclosures so that they run overnight. It's true that the wire that I fitted can definitely carry more than like 10 watts, but it will still fail first in a failure event, like in a sort of high current catastrophic failure event. So it will still protect the rest of the traces that would otherwise be carrying the current. And the fact that that bit of wire that I fitted does have a bit higher current capability should mean that if for some reason somebody accidentally, like for like a fraction of a second, touches 12 volts power wire onto the speaker negative terminal, for example, or the case. That's the most common thing, is it touches the case or something like that. If for some reason there is a high current spike between the two ground points, that piece of wire being there won't fail as instantly as the little 1/4 watt kind of jumper resistor would do. So it gives people a bit of a second chance, and doesn't then separate the output side ground from the main side ground instantly. There needs to be like high current kept on there for like a good few seconds in order for that to fail. This was a ZX-1500.1. Eberg says, I'm trying to get these cab 45 done so I can go build my greenhouse. Nice. Hopefully they're pretty simple. Yeah, cool. Right, I'm going to go finish the thumbnail for Boom or Bust episode 7, which is coming out tonight. Subscribe if you're not already subscribed to get a notification, hopefully, about that when it comes out. And I'll see you in a stream, possibly tomorrow, possibly a little bit later on this week, depending on how I get on. Thanks for keeping me company with this one, guys. Hope it was entertaining and educational. And we'll see you in the next one. Bye.